Good afternoon, everybody. Hello. My name is Carol Oliver. I'm a researcher with the Australian Centre for Astrobiology at the University of New South Wales. I know that we've got a lot of general audience here, but we also have a lot of people from an astrobiology conference that's happening at the University of New South Wales tomorrow and the next day. So first of all, before I begin this, I would just do some housekeeping for those conference delegates. So please excuse me, general public. First of all, to say that the conference for those delegates opens at 5 to 9 tomorrow at UNSW, and it's in building E27. It's the Biomed Theatres, and you can enter by gates 9 or 11, however you arrive there by taxi or by bus. The program is on your USB sticks, which come in your badges here, but you might not have a computer with you. So just to let you know those things, and we'll have a program ready for you when you arrive. Also, for everybody that's here, on Tuesday, Professor Roger Summons from the Mars Science Lab, that's Curiosity on Mars at the moment, will be giving a talk at 6:30 in the Law Theatre, which is the lower campus. So you come in the main entrance on Anzac Parade, and you just walk up the big main path, and you'll come to the Law Theatre on your left. So that's Tuesday at 6:30, talking about the Mars Science Lab, Professor Roger Summons. To remind you also that even if you're general public or even if you're a delegate, you need to RSVP for that online through the university website. That's just www.unsw.edu.au or through the Australian Centre for Astrobiology website. Okay. To begin, SETI, as I'm sure you all know, you're aware, is the scientific search for extraterrestrial intelligence. It's the premier organisation for undertaking this over a very long period of time at the SETI Institute in California. And it is where Jill Tarter has led the project through its Project Phoenix days to the building of the Allen Telescope Array, which I'm sure she'll be telling you about. SETI has a close association with Australia. I first met Jill in 1995, and we're just counting up the years, 23. And it was on a very wet and uncharacteristically windy day in the middle of a sheep paddock at the Parkes Radio Telescope. And they were, the SETI Institute was there to undertake Project Phoenix for 6 months. A young physicist at my then university, Dr. Bobby Vale, was a volunteer observer on that project, and I was there as the University of Western Sydney's science journalist to promote Bobby's role in the project. Jill patiently fielded media at the beginning of this 6-month project, but at the end of the Parkes stint, she was much more reluctant with the media. She did not want to see media stories of failure, preferring to head back to California without a fanfare. I had an obligation to Bobby and to the university to get that media in, and Jill wasn't taking my calls. So I thought, well, the only way to do this was to go to Parkes and catch her in the middle of an observing session, which I was certain she'd be doing by herself in the Parkes Radio Telescope. And I was right. So at 3 a.m. I went from quarters down this 1 kilometre dark road, snakes around and everything, my sights set on the telescope and with my mission in mind. And I did actually persuade Jill to undertake that media, and she reluctantly agreed. But as is so characteristic of Jill, and we were bringing the media in that day, she finished her observing session, and the sun was coming up, and she was on her way down to town to get dinner food for 30 guests that evening, including the media. And she not only did that, but she came back and she made dinner, and then she fronted it up to the media. But as a result of that, we were put in a position of the very good stories that came out of it that allowed us in later years to house an Australian SETI project on the Parkes Radio's telescope, Southern Serendip. And that went for a number of years, and we still have to analyse some of the data from that, but we're getting to that. Jill, in the meantime, has gone on to be an icon at SETI. Her life was broadly characterised in Jodie Foster's lead role in the movie Contact, and in 2004 was named by Time magazine as one of the top 100 influential people in the world. She's the outgoing director for the Centre for SETI Research at the SETI Institute and holds the Bernard M. Oliver Chair there. No relationship to me, Oliver. She holds several NASA Public Service Awards and is a fellow of the American Association for the Advancement of Science and the California Academy of Science. Among many other honours, she also holds the 2009 TED Talk Prize. So I give you Jill. Jill.
Well, thank you all for coming out on a Sunday afternoon to listen to a talk. And Carol, thank you for reminding me of where we met and all those days at Parkes. It was a lot of fun, great telescope. And I've been back to Australia lots of times since then and love it every time I come. So I'm just going to try and give you an update on where we stand on this really old question. Are we alone? So for millennia, humans have been on a journey to answer questions about who we are, where we are, why we are, what should be, what is, and of course the question is anybody else out there? And every journey has a beginning. And so I'd like to invite you this afternoon to come on a journey with me, hopefully changing your perspective a little bit along the way. So we're starting our journey from someplace. We're starting it here. Actually, today it probably looks a bit more like this, right? So we think of ourselves as being here with our newly found skills at Google Earth. We can recognize ourselves as being here. From the altitude of Earth observing satellites, we'd see ourselves as here. And since 1968, when astronaut Bill Anders took this picture of Earthrise, we have begun to realize that we are in fact here in the darkness of space. When this Cassini spacecraft turned around and looked homeward, it actually saw us. You can see the white dot. That's us. We're here. And Voyager 1, on its way out of the solar system, turned around and looked homeward and saw us in the zodiacal dust, our pale blue dot right there. We're here, the outskirts of a beautiful spiral galaxy, which would look like this if we could get outside and look back. And of course, we're here. So over the journey, we have learned that we orbit a star that is one of only 400 billion stars in the Milky Way galaxy, and that galaxy is only one of at least 100 billion galaxies in the observable universe. The truth is that we're made of this. This is the remnants of a supernova explosion. This is the stardust from which we are made. It really takes a cosmos to make a human being. And the iron atoms in the hemoglobin molecules running around your bloodstream were manufactured, were fused together in the heart of a massive star that blew up something like 8 billion years ago and produced this beautiful stardust which turned into us. So from my perspective, we live in a fragile island of life, but within a universe of possibilities. and just how exciting and broad those possibilities are is brought home to us by studies of organisms such as these extremophiles that live in environments that are hugely hostile to you and I. But they're environments for which these organisms are phenomenally well suited after millions of years of evolution. And so one of the lessons that I've learned over my scientific career is that this idea of the ascent of man, of humans being the pinnacle of evolution, is just totally wrong. Nature has been evolving organisms phenomenally, beautifully, to fit into a much, much wider range of environments than we once might have believed. So I think the microbes are finally beginning to get the respect they deserve. And we're now thinking about life and potentially habitable real estate beyond the earth that isn't just about nice, warm little ponds, right? Life may, in fact, inhabit environments extremely different from a rainy afternoon in Sydney. In fact, although we're not able to find life right now, we are looking for the conditions where life might once have existed here in this cold desert. Now, this is not the Mars yard downstairs. This is the real thing, right? So this is Gale Crater. This is brought to you by the wonderful laboratory that we call Curiosity. I think it is amazing that we are looking at this real estate far beyond the surface of our planet in a way that gives us a view that is not so unusual, not so unimaginable. It is another world, but it is a world that we can recognize, a world that once might have been much more like our planet billions of years ago. And so we might find, and we have already been finding, and you'll hear more if you come listen to Roger's talk, we're finding that conditions on early Mars were in fact wetter and warmer and potentially like conditions on the early Earth. And so life might have started on Mars. Conceivably, even today, could be continuing to exist in some liquid aquifer deep beneath the surface of the planet. But we are beginning to look for life, not only in the most hostile environments on our own planet, but beyond our planet on Mars. And we're thinking about life on some of the giant moons out there in our solar system. Ganymede and Callisto and Europa, ice-covered bodies, large moons orbiting Jupiter. Beneath those icy carapaces, those icy crusts, we believe that there, at least on Europa, liquid water, salty oceans. Perhaps twice as much water on this moon that is about the size of our moon as there are on all the oceans on this planet. Lots of water. It's been there for billions of years. Maybe, just possibly, there could be life of some kind on Europa, or Ganymede, or Callisto, or the icy world giant moon Titan that orbits Saturn. And even, look, this tiny, tiny little moon Enceladus that orbits Saturn. And we thought, oh, boring, right? Total little body. But look, this is erupting with ice volcanoes, with geysers that are full of water and organics. Maybe even a tiny little body like Enceladus could prove to be habitable for some sorts of life. So we've got decades worth of exploration ahead of us in our own solar system, and it's really exciting to think about what we might find on these other worlds. But we're also thinking about worlds beyond our solar system. In 2009, we launched this spacecraft called Kepler, whose job it is to find small Earth-sized planets in orbit around distant stars. And Kepler does this by staring at 100 square degrees on the sky, about 1/400th of the sky. Put up your hand like that, your outstretched hand, that's about 100 square degrees on the sky. And in that region, just above the plane of the Milky Way galaxy, there are 4.5 million stars, 150,000 of which have been chosen by Kepler to be observed continuously. Now, those rectangles on the screen represent CCD arrays. Did we just lose the mic? Hello. Are we back? Yes. All right. So Kepler uses CCDs, the same sort of thing that you find in your cell phone camera. But it doesn't have a 2 megapixel or a 10 megapixel camera. It has a 93 million pixel camera. Very, very sensitive CCDs. And it looks at those 150,000 stars continuously, and it waits for one of them to become dimmer, to blink. Why might a star blink at us? It's because if the star and any planets around it are oriented just right, then the planet may pass in front of the star, and Kepler may see some of the light from the star being blocked. So that graph on the bottom shows you a light curve, the intensity from the star at the beginning, dipping down as the planet passes in front of it, and rising up again as the planet goes off the surface or the disk of the star. Now that graph makes this look like an easy job. So we ought to be able to find planets that are transiting in front of these 150,000 stars. No problem. Well, indeed, it is a problem. It's very difficult. When a planet like Jupiter passes in front of a star like the Sun, Jupiter will block about 1% of the light from the Sun for hours. Now, that's an easy measurement. But when it's a planet the size of the Earth, it only blocks a few parts per 100,000 of the light from the star. So finding small planets like Earth is really, really difficult. It's one of the reasons that it took almost 25 years to the day from the first paper on transit detections to the launch of Kepler. Really, really hard to make those sensitive CCDs and build a spacecraft that could look at all these stars all the time and see these small dips. Well, it turns out it works. And there are a number of stars that are winking at us. As of today, when I looked at the Kepler website, there were 3,216 planetary candidates detected by Kepler. So far, 132 of them have been looked at with ground-based telescopes and confirmed to be planets. We don't have enough ground-based time on telescopes, and some of these stars are too faint to allow confirmation of all of these candidates, but we can work statistically, and we figure that less than 10%, probably more like 5% of these candidates will turn out to be false positives. These really are other worlds out there. And indeed, when you try and look at how far the planet is from its star, how much sunlight or starlight it might be receiving, something like 58 of these appear to be at a distance from their star, which is not too hot, not too cold, but maybe just right for having liquid water. So we call this the habitable zone because life, at least life as we know it, is all about water as a solvent. And so Kepler is showing us other systems, most of which are extremely different from our own. So before Kepler, before 1995, when we found the very first planets orbiting solar-type stars with radial velocity measurements, we'd make models, all right? We didn't know whether planets were plentiful or rare, but we tried to build planetary systems in our computer. And you know, somehow, when we put the input in and we looked at what we got out, well, all of the planets were going around in circular orbits. The big gas giants were always on the outside, and the little rocky planets were always on the inside. And so we just had this feeling that the planets out there, if they existed, their systems would be just like ours. Imagine our surprise when the first planet that was detected was more massive than Jupiter, and it was so close to its star that its orbital period was only a little more than 4 days. So what's been wonderful about the data from Kepler, particularly those multi-planet systems, are what Kepler is teaching us about different ways to make planetary systems. When you only have one example, you're likely to fool yourself into thinking you know more than you do, which is the case when we used to model other solar systems before we ever found any. And here in these multi-planet systems, we're seeing orbits and behaviors totally different from our own solar system. And in particular, we've learned a very important lesson, which is that planets don't stay where they're born. Some of them migrate from outside in towards the star. Some of them actually fall into their star, and some of them stop in 4-day periods before they get there. Others are kicked out like a big, huge billiard game. And there are planets now that are being thrown out of their birthplace, and there are some people, perhaps many people, who suggest that there may be more rogue planets wandering around in interstellar space, more planets that are rogues even than planets that still remain within planetary systems. So we now know that planets are prevalent. And that's important because life as we know it is a planetary phenomenon. And we think planets are a good thing for life elsewhere. What we are doing is being able to find smaller and smaller planets at larger and larger distances from their star. We're beginning to close in on Earth 2.0, an analog of our planet. A planet that's Earth's size. If we can do radial velocities, we'd like to find out that it had Earth's density. It's a rocky planet. And it was just at the right distance from its star, a star similar to our sun, for there to be liquid water. So Earth 2.0, we think, is in the future. Everyone that I know that is working on exoplanet studies can almost taste it. We think it's in our data. We think that this is an announcement that you'll be hearing very, very soon. And what would happen if we announce right there, up there, point your telescope, that's a planet just like ours? Well, I think that there would be 2 questions that people would ask immediately. Can we go there? Well, if it's in the Kepler field, not likely. It's going to be hundreds or thousands of light years away. But if it's found by radial velocity studies, it might be nearby. It might, in fact, be a destination. And I'm actually working with a group that's led by Mae Jemison that's working, it's called the 100 Years Starship Study, a group that's working on solving the technology challenges inherent in building a starship something like a century from now. And not only the technology challenges, but the human challenges, the governance. How do we all get along on a spaceship on a very long journey? And it's really exciting. I just spent the time before the lecture looking at the design display across the way. because one of the funny discussions we've been having is that if you're on a starship, a closed environmental system, fabric is one of the more toxic things you can have on your starship. If your fabric is organic, you have to grow it or feed it, and that takes fertilizer or some other kind of food. You have to dye it, you have to manufacture it, you have to wash it. All toxic enterprises in a closed system. So we've been starting to think about, well, maybe what we should do is just engineer skin instead. Put chromophores in the skin so you can dress yourself as a butterfly if you'd like, or toughen up the skin so you won't get cut, or you can keep warm. Interesting questions. We don't know whether indeed we will ever be able to go to the stars. We don't know if there's some physics that precludes it, or if it's simply technology and will to go. But we're working on that problem. So I think that's the first question. Earth 2.0, can we go there? What's the second question? I'm pretty sure it's going to be, does anybody live there? And at least for the next decade, until we can build some other new instrumentation, SETI is about the only game in town to answer that question. We call it the search for extraterrestrial intelligence. In fact, that's not quite right. We don't know how to define intelligence, and we don't know how to find it at a distance. So what we're doing is we're looking for technology. We're looking for something that modifies its environment in ways that we can actually see across interstellar distances. So we should really call it the search for extraterrestrial technology, but SETI got in there early. It's got brand recognition, so we're not going to change it. But we're looking for technology. And we started that journey using the tools that were left over from the radars that we developed in World War II. We began to use radio telescopes to look for evidence of signals from someone else's technology. And more recently, when the detectors got to be affordable, we started to look for optical signals, bright white light flashes that last a billionth of a second or less, that might be from pulsed lasers that are focused by large collectors and sent our way to attract our attention. So we're looking for Earth 2.0, and for me, Earth 2.0 would have another attribute. It would have technology, such as we have. And it's not an unreasonable thing. There are many technologies that we use today that, in fact, could be detectable over interstellar distances. And so they might be doing something. Interplanetary communication, a huge shield to guard against asteroids, or something we actually can't even begin to think about. But if we looked, we could recognize it. And that's what we're doing in SETI. Now, whether or not SETI is going to ever succeed depends upon whether anybody is out there. Are there any other technological civilizations? But it also depends, crucially, on the longevity of those technological civilizations. So if we're going to detect anyone else, it means that we have to be close enough in space so that our instruments are sensitive enough to detect their technology. But the thing we usually don't think about is we also have to be lined up in time. We ourselves are a very young technology, about 100 years old, in a very old galaxy. Our galaxy is about 10 billion years old. Now, if technologies out there don't last for very long, then there's no probability that any two technologies will be close enough in space and overlap in time to be detectable. So technologies have to last for a long time, and it's longevity that is the key to success in SETI, which is why Phil Morrison, wonderful physicist,
used to refer to SETI as the archaeology of the future. By that he meant any signals we receive are traveling at the speed of light, which is finite, and they're coming from a long way away. So if there's any information in those signals, by the time they get here, they're going to be telling us about their past. But the fact that we succeed in a detection tells us that indeed we can have a long future because technologies are long-lived on the average. So we've been doing this search since Frank Drake made the first radio observations in 1960, so a little more than 50 years. Sounds like a long time. So how much have we searched? Well, the search space that we're looking through is multidimensional. We don't know what frequency, what direction, what time, what polarization, what modulation. It's actually about 9-dimensional. So if I set the volume that we would like to explore to look for other technologies in the Milky Way galaxy, if I set that volume equal to the volume of the Earth's oceans, then in 50 years we have sampled 1 8-ounce glass of that cosmic search ocean. And it doesn't sound like very much. And believe me, we've been working on this. We're not sloughing off here. But we've been using the tools of the astronomer. We've been using tools that haven't necessarily been optimized for doing the SETI search. And if your question was, are there any fish in the ocean? And you did this experiment, you scooped up a glass and you're looking in your glass, no fish. Well, that experiment could work. There are fish that could have fit in that glass. But if you don't see any, I think you're probably going to conclude that you haven't sampled enough of the ocean, rather than to conclude on the basis of one glass that there are no fish. So what we need to do in SETI is to build bigger glasses, glasses that we can dip into this ocean faster and sample more and more and more of this ocean until we have done a search that's big enough to be commensurate with this amazing question we're asking, are we alone? And so here's one of the glasses. It's the one that I've been working on in Northern California, the Allen Telescope Array. Currently, it consists of 42 telescopes. With time and funding, we hope to grow it to 350. It's a way of building a large radio telescope using a lot of computing and small dishes to tie them all together to make something that can look at a big area of the sky with a lot of sensitivity. And so we dedicated this array in 2007, and in 2011 we began using it to target those exoplanetary systems that Kepler and the radio velocity teams have been finding. And one of the key pieces of technology is a feed and receiver system in these telescopes that can cover a huge range of frequencies. And we built this system. We built the array with the first generation of these receivers. It looks kind of like a Flash Gordon death ray, right? And the size, the scale of those pennants represent the kinds of wavelengths that we can detect. And so going from the very big low frequency to the very tiny high frequency, with the original feeds we could look at all frequencies or wavelengths from 500 megahertz, half a gigahertz, up to 10 gigahertz all at once. And we did a pretty good job, but we had more noise than we wanted, which meant that it limits the faintness of the signals that we can see from the sky. So right now we're engaged in an upgrade. We chopped off the big end of that feed, and we made the small end a bit smaller. So now, and then we put it all in a bottle and are cooling it all down. So now we're retrofitting those 42 telescopes with these new feeds, and they will go from 1 gigahertz to 15 gigahertz and open up a different part of the phase space for us to observe, and with about at least an improvement of 2 in the system temperatures that we will achieve. So we're really excited about that. We're also excited about using computing in different ways to look for different kinds of signals with this radio telescope. And for us, what we're doing is we're looking for narrowband radio signals, the kind of thing that we can do with technology, but nature never can. Here's a two-dimensional diagram where frequency runs horizontally and time runs vertically. And I don't need to tell you anything more than that. And you can see in this slide that there's a lot of stuff that looks like noise, snow, and there are very non-noise-like something going on here. This, in fact, is what the planet Mars looks like to us sometimes when we turn our radio telescope in that direction, and both the Mars Reconnaissance Orbiter and Mars Express happen to be on our side of the planet and transmitting. So we're looking for engineered signals, things that don't look natural, things that occupy a very small band in the radio spectrum. And it works really well. Here's another diagram, right? The same thing, frequency versus time. And there's a signal in there. I could talk a little longer and maybe your eye would pick it out, because once I show it to you, you'll not be able to not see it. Does anybody see it? All right, there it is. All right? And it's hard for your eye to see that, but our computers have no problem whatsoever. We programmed them to find exactly that kind of pattern. And so this is a 6 sigma detection. And it's coming from the most distant human object. This is the Voyager 1 spacecraft, which is leaving the solar system. If you looked at the cartoon, what is it, XKCD, thank you. A couple of days ago, it was chalking off the number of times Voyager 1 has left the solar system, right? Because we keep expecting, it just, no, we think we're almost there. Anyway, it's a long way away, 100 times, more than 100 times farther away from us than we are from the sun. And it's only got a 6-watt transmitter on board. 6 watts? That's the amount of power in the tiny little white Christmas tree lights that we love to string up, right? It's got a bit of gain, but still, it's a weak signal coming from a long direction away, a long distance, and yet we can, in fact, find that signal very easily with our computer programs. So, as I've already said, we're using the Allen Telescope Array to look in the direction of the Kepler field, all those exoplanets. And the array is an interferometer, which means it's a radio camera. It actually looks at a big patch of the sky, and in that patch of the sky there are 1,250 pixels, and each pixel has 1,000 frequency channels that we can look at. And so we make radio images of the sky, and we're finding new ways to look for signals with that camera. But our bread and butter is to pick out 3 of those pixels at a time with things that we call beamformers. And then behind those chosen 3 pixels, we put spectrometers that have hundreds of millions of spectral channels, not just 1,000, to look for these narrowband signals. And we use the 3 different exoplanet systems as a test to see whether the signal is really coming from one of those 3 directions, or whether it's coming from interference that we create, our own technologies. And every day, we're looking at these signals for 12 hours at least a day. If you want to follow us and you have an iPhone, you can get this app called Distant Suns, and there's this little green radio telescope, and you punch that, and you see the 3 directions on the sky that we're observing at that moment. Or if you want to get more involved, and I hope some of the young people in the crowd we've launched a citizen science project called SETIlive.org, where we take a tiny little bit of the data from the Allen Telescope Array, put it out in real time in the cloud, we present it to volunteers, and we let them look for signals with their eyes, patterns that are different than straight lines, things that we haven't programmed our computers to find. And the pieces of the spectrum that we send out are the ones that are the most crowded, that have the most signals, so that our automated programs can find all the signals in real time, but they just don't have time to classify them all and to figure out whether it's a signal we've seen before, whether it's a signal that's coming from the equipment in our own control room, or something that might in fact be extraterrestrial. So we're asking the public to help us with this. And I think we'll get a lot more traction when we can figure out a way to put this on a small screen. Right now it's browser-based. But when we can put it on a small mobile platform, I think it'll be a lot more fun for you, and we might get a lot more searching done for us. So we're also, as I've mentioned, doing optical SETI. We're primarily doing that at universities with meter-class optical telescopes that are looking for these bright flashes. We have detectors that count the number of photons arriving every billionth of a second, every nanosecond. And we can look for clumps of photons arriving when you don't expect even one to be coming from the star at this fast rate. And these, as I said, they're being done at universities like Harvard, Berkeley, the Lick Observatory. They're actually also an optical SETI program being done here at the Campbelltown Rotary Observatory, the University of Western Sydney. So although the Southern Serendip that Carol mentioned is not on the telescope at Parkes at the moment, there is some optical SETI going on in Australia. And what could we set a limit on? What could we detect with the optical SETI searches that are being done today? Well, we could detect the transmission from our strongest lasers. They're the ones that have been developed at Lawrence Livermore lab for the ignition, the National Ignition Facility, to do fusion. It's an opportunity to try and develop fusion power. These really, really powerful petawatt lasers, if they were focused by a 10-meter telescope, we could detect those 1,000 light years away. Similarly, in the radio, we could detect the strongest transmitter that we have on the planet, which is associated with the radar at the large telescope in Puerto Rico at Arecibo. We could detect that to 1,000 light years if it happened to be pointing right at us. And what does that mean, this detection limit of 1,000 light years? Well, there are about 1 million stars within that volume that we would be interested in studying. And so I told you that longevity was the key to successful detection. And if I'm to have any kind of a chance of detecting a technological civilization by probing 1 million stars, on average, technologies are going to have to last 100,000 years or more. So we're really looking to see whether anybody can make it to that long future. So beyond what we're doing now, the James Webb Space Telescope and its whatever follows on will launch, and it will be used to look for biosignatures. The trick is to try and make an image of these Earth-like planets and then do a chemical assay of their atmospheres to say, is there some disequilibrium chemistry going on that we can't explain any other way than by having biology on the surface of the planet. Now, this is a really difficult job, and we're going to be talking about this at the next couple of days at the astrobiology meeting. So what is it that life as we know it and life as we don't yet know it, how can it make its presence sensible by changing atmospheric chemistry. If you looked at the Earth from a large distance, you would see that we have simultaneously in our atmosphere molecular oxygen and methane gas. Now, in the laboratory, you put those two things together and they instantly want to become water and carbon dioxide. That's happening in our atmosphere all the time. But on the surface of the planet, we have photosynthesis from all of the plants, as long as we don't cut them all down, right? We've got oxygen-producing plants on the surface of the planet, and we've got methanogens in the guts of termites, and we've got bovine flatulence, cow fart, right? It's putting methane into the air all the time. So it's recombining, but it's also being resupplied from the surface. That's a very definite biosignature from the Earth. So could we find similar signatures from planets around other stars? Big question, because it's hard to come up with something that everyone will agree, you can't do that without biology. And of course, you're also trying to talk about biology that we don't yet know about. A different kind of biology, perhaps, some other kind of life. Nevertheless, we're going to go looking for biosignatures. And if you find them, you won't know whether you necessarily found the microbes or the mathematicians. So we still have to keep doing SETI in the future. And we look to these next generation of instruments, the European Extremely Large Telescope for optical studies, the Square Kilometre Array here in Western Australia and in South Africa for radio SETI, to be able to see farther and detect fainter and fainter signals in the future. And the reason that I like to come to places like Sydney, well, of course, who wouldn't want to come to Sydney, right? I love coming to Sydney, but I like going around the world talking to people about this project because I want to change their perspective. I want to think with them about this journey and being here and what really we mean by here. I want people to open their eyes and look at themselves from a different perspective. And I think that's what SETI does. If you start thinking about an independently evolved, intelligent species out there, I think it holds up a mirror to everybody on this planet and forces us to see ourselves as all the same and trivialize the differences among humans that we find so difficult today. So I think even if SETI never detects a signal, if in fact we can get everyone on the planet thinking in this more cosmic way, then we will have done something incredibly profound. And it's exactly what we need to do to start working on the challenges that we face today that don't stop at national boundaries. It's what we need to do to figure out how to adapt to rapid climate change, to keep our sources of water and food protected, to continue to maintain biodiversity on this planet. We have to think more cosmically. We have to see ourselves in a different manner. And if SETI can help with that, I think we will have done something marvelous. So thanks for listening to me.
Does anybody have any questions of Jill? We have some microphones around the room. Just put your hand up.
Yeah, there's the assumption behind that any signal we pick up is deliberately beamed. And in that case, there's a sender and a receiver. Now, you've given the analysis from the point of view of the receiver looking at exoplanets. But if you take it from the point of view of the sender, it's a narrow beam, you know, whether it's a radio telescope or a laser, And isn't he going to want to transmit in a direction where people will be looking back at him at the time the signal arrives? In which case, it seems the only way will be to transmit directly away from a gamma ray burster, which everybody in the galaxy is going to see. And the second thing is, as for noticing signs of other civilizations, there was, back in the 60s, I think the Russians were very keen on SETI, and they gave up when Kardashev came up with the point that within 3 to 5 million years of a technological society in a galaxy, it would take over the entire galaxy, and its need for energy, whatever it was doing, would make a mark that would be visible across the entire universe. And we've looked at millions, billions of galaxies, and there's no sign of anybody out there.
Okay. Let me take that second question first. So you're talking about Kardashev's approach to labeling advanced technologies in terms of the power they consume or can manage. Type 1, we're not even yet at a type 1 ourselves. Type 2, type 3. Type 3 can have control over the amount of power that's emitted by their entire galaxy. Okay, I'm almost not kidding here, but there's something that we've learned since the days of Kardashev. What's dark energy? What's dark matter? Might either of those be a manifestation of an extraordinarily advanced civilization able to manipulate a great deal of energy? Think about it. I'm not saying that that's the answer to dark matter and dark energy, and there are lots of people who have more mundane explanations. But you know, when Kolya and I talk about this, Kardashev and I talk about this, it isn't clear that you would notice that advanced technology because they may, in some sense, have already left the galaxy, moved into another one of the 11 dimensions that we think are now part of our universe. So it's not clear what a type 3 civilization would look like. Kardashev had a very specific idea when he started, but now all of us have had broader thinking about that. And your first question about beaming and the strategy, which is that the right way to point your beam as a transmitter is to point it in the opposite direction from some amazing astrophysical phenomena that everybody will be studying, right? And so you end up in the, as a receiver, you end up in the beam of that transmitter. If we ever start to transmit, that might be a strategy that we adopt. Certainly, I think that our astronomers and astrophysicists would have a good chance of serendipitously stumbling on such a transmission strategy. We've also tried it occasionally with our telescopes. But there's also the potential for having an omnidirectional or a fan beam signal, not necessarily a narrow band or a beamed narrow signal. So that's a good suggestion. It's one of the strategies we've tried. Right now, because the exoplanets are finite and we can do that particular survey in a few years, that happens to be the strategy that we're concentrating on now.
Do we have another question? Down here, Max, sorry. Would you speak up?
No, here's a microphone for you.
I was going to ask if you today were alerted to the fact that we had discovered a signal from extraterrestrial environment, which was obviously intelligent, what would you do?
Well, at the SETI Institute, we plan for success. So I can tell you at the observatory and at the Institute, there's champagne on ice. And I'll tell you, after I go, holy shit, what have we just found? It's going to be, let's drink some champagne. But after we get through that, and hopefully not too much of it so we can still think straight, there's a whole protocol of things that we would like to do. And the major concerns are to make sure that the target, the area on the sky, the object that we think is transmitting, continues to get observed after it sets. Because unless it's circumpolar, it's going to set at the discovery site. So you want to call up, our favorite example is from Northern California, we call up the Australians, right? And we say, would you take a look at this and would you continue to observe? And we do that for a second reason, and that's the other concern is to rule out a deliberate hoax, right? Because if you can find the signal with equipment we didn't build, software we didn't write, you can find it independently, then that's probably the best guard against deliberate hoax. So we will call up the director at Parks and get a little bit of quiet discretionary time from the director, ask them to check it out. It might not be possible. We might discover a signal at a frequency where no one else has a receiver on a telescope, or no one can fit us in, or that independent confirmation just might not be possible. But we'll try for it. And then the other thing we're going to do is send out an IAU telegram. Obviously, not a telegram anymore, but it's a web-based system, which alerts all the observatories. All the observatories in the world subscribe to the IAU telegram system. And it will tell them about what we've discovered. It will make the discovery data available to this community of astronomers for two reasons. One, we hope that they'll use whatever equipment they have to look and see if there's anything more that we haven't found yet. And two, because when we do the next step, which is to hold a press conference to tell the world, that they can all serve as the regional resource for their media. Right? So the world's journalists and bloggers aren't going to be able to call up the discovery site and tell me about what you found, right? It's just not going to happen. So if we can make that discovery data available to a community globally who is probably best trained to interpret it for their local media, then maybe we can get the right story out as opposed to one that the journalists need to invent in a vacuum. So those are some of the things we've thought about. But the champagne sure comes first.
Are there any other questions? Yes. This one down here.
That's all right. I'll hear you, but they won't back there.
How prolific do you personally believe life is in the universe?
Well, as a scientist...
Sorry, intelligent life, I should say.
Yeah, okay. As a scientist, my whole approach to this is to replace the verb you just used, which was believe, with explore. I want to figure out what is out there. Whatever I think really makes no difference. The question is, what is? What's the reality? So that's what I do as a scientist. And I don't know the answer to the question.
Did we have another question over the back?
Uh-oh, I'm in trouble now.
No, you're not. You mentioned the square kilometre array that's under construction in Western Australia and South Africa. Would you like to enlarge on that and say something about the frequency ranges that are being targeted by the SKA and whether that's useful or not, and just what role the SKA might play in the SETI search?
Well, one of the fundamental science cases for the SKA is the cradle of life. So observing the universe to see what kind of biomolecules are being created in the molecular clouds between the stars, understanding the delivery system, how some of those biomolecules might have been delivered to the nascent Earth and to other planets. And we also hope they're going to do SETI. And Malcolm knows that the US was involved in the Square Kilometer Array. I think I started with that group in '96 for a long time, until it got to be all about real money, and then the US said, oops, we don't have any, we're out of here, which is sad. So certainly back then, while we were still involved, I was always beating the table about having extra beams to devote to SETI searches. I hope that still keeps to be as part of their science case. Certainly as an astrobiology instrument, I think it's going to be extremely useful to understand exactly how this poetry works. I mean, we have this wonderful story we tell ourselves about the building blocks of life being ubiquitous everywhere. They're built in these large molecular clouds. It must be everywhere, but it's kind of hard to get these big molecules from there to here in one piece in a way that makes sense through the accretion shocks that surround the formation of a new planetary system. And so there's a lot that we need to learn about exactly whether that's just poetry or there's reality. And that will tell us whether or not Christian de Duve was right to say that life is a cosmic imperative. So we need to go from the believe, right? We believe these building blocks of life have something to say about life on this planet or other planets, to the reality of actually what the delivery mechanism is. I think the SKA can help with that.
Okay, I think we'll end it there. And in a moment, I have a few more announcements. But at the moment, I would like to very much thank Jill for a wonderful talk and for coming to Australia to give it to us. Thank you. So,
you're welcome. You're welcome. Do I just open this? Can I open this? Oh, I never could wait for my Christmas presents, so let me open it, Carol, so I can thank you properly. Australia's greatest inventions and innovations. Phenomenal. Thank you. I will read this with pleasure.
Okay, for the few announcements. For the astrobiology delegates, there are some refreshments just outside the Target Theatre, which is the next theatre along. For everybody who's here, I invite you to the Mars Yard downstairs to view it. It's the result of a partnership between the University of New South Wales, the University of Sydney, and of course the Powerhouse Museum. And is used for both research and education from high school level to doctoral levels. So please take a moment to go down there on the ground level, and thank you very much for attending this afternoon. Thank you.